just want you guys to learn stuff, man. Here, let me know if, I think there's no typos in that one, but.
Yeah, there's a typo.
No. Well, let me know what it is so I can replace it.
Here you have, on the first question, you have n equals t prime minus t prime. It should be n equals t minus t prime.
You guys will catch that one. So we derived this path integral last time. This is the imaginary time. So it's Wick rotated from real time, if you want to call it that. The boundary condition, because your partition function is this if you will trace or sum over diagonal matrix elements or something like that. So in order to keep the matrix elements diagonal, there's a boundary condition at tau equals beta. And that boundary condition is reflected in this condition on the functional integral, where your field at beta is rho, times your field at tau equals 0, and rho is that -1 for fermions and +1 for bosons. That's your functional integral. It's like the product of all of those discrete resolutions of the identity that you've inserted. And this is the Hamiltonian formulation. Okay, so it's the field and its conjugate, the time derivative. We'll talk about that a bit, or the tau derivative here. And this in combination with the Hamiltonian, which I called tilde, which has a chemical potential in it, remember, for grand canonical ensembles, we just wrote as the action. So that was, it's nice, a nice compact notation. I guess we're going to ask today a little bit about, what are these path integrals good for? So in some, you've derived another formulation, a very a foundational formulation of quantum mechanics. Quantum mechanics can be described in terms of path integrals instead of operators, and so on. But that's not why we necessarily use path integrals in many body systems. So something we'll talk about a little bit later in the course, but let me just mention it briefly now, is path integrals set us up well for perturbation theories. And by perturbation theories, I usually mean when our action can be written as, I think we'll usually write them like this, something that's non-interacting plus interactions. So when essentially your Hamiltonian is quadratic in the field operators, this is the non-interacting case, and this is when we can do Gaussian integration. So typically for non-interacting systems, you can take the path integral and solve it exactly. And when you start adding interactions, you can't do things exactly anymore. The transverse field Ising model is an example of an interacting Hamiltonian. But even though you have interactions, you can typically do a perturbation theory by taking expectation values over the non-interacting action, if you will. So you can break up your field theory into a non-interacting expectation value plus, perturbatively including interactions. And that's something we'll deal with when we talk about 5-4 theories later in the class. So I'll continue the sort of abstraction of the path integral later, and we'll add interacting terms of the Hamiltonian, and I'll show you how these add fourth order, essentially field terms. And this is where Feynman diagrams come in. You ever do perturbation theories, Feynman diagrams? So the path integrals will set us up for that. And they're also good for calculating correlation functions, especially in the Gaussian case. And correlation functions are the central object that you're typically interested in quantum many-body physics, I guess, condensed matter and so on. So these are related to physical response functions. Correlation functions are correlations, expectation values of operators, and the operators can occur at different, they can be different operators, number one, and they can occur at different times and different spatial positions. So I don't know. Let's say R2, T2, 1, R1, T1. That's a general form of a correlation function. And that expectation value, once we have the path integral for the partition representation of the partition function, the expectation value of any operator is just this normalized trace over, I'll say those same operators. E minus beta H tilde, where these are just operators. So we can essentially write the expectation value as a path integral, which I'll do today, in the same way that we just wrote the partition function as a path integral. And then especially if we're Gaussian, especially if our Hamiltonian is quadratic, we can do the Gaussian integral and get exact expressions for those correlation functions. So just a note on the correlation functions. So physical responses are related to correlation functions. By response functions, I mean you take your system and you perturb it or you probe it with something like maybe a magnetic field or some time dependent operator or something like that, and you look at how the system responds. So most of the relationship between response functions and correlation functions comes from linear response theory. So if you're in condensed matter, this is the main point, I think, of a lot of what we do. And you might be familiar with some examples. So if you have a spin coupled to a magnetic field, you can probe the response of that spin to that magnetic field, especially if that field is something that's time dependent. I can say R and T. And you can quantify that response with a correlation function. That's just a spin-spin correlation function. So those are spin operators. And if you Fourier transform that into momentum and frequency space from real space and time, gives you, so I want momentum, what am I calling it? I guess P. K would have been better, and frequency. which is just a dynamical susceptibility. So the dynamical susceptibility is a response function, but it's probed with a two-point correlation function. Transport coefficients are another example that you might be familiar with. Transport coefficients, they characterize dissipation in the system. So if you have some sort of current, if you have some sort of voltage and it produces a current and so on, you want to measure transport. Or you want to take a material and ask about its transport properties under application of whatever external sort of stimulus. The dissipation of the current or the dissipation of transport is specified by essentially matrix elements of an operator like this. So these types of correlation functions, if it's a single operator, it looks like a fluctuation. So you can say a matrix element of the thermodynamic fluctuation. That matrix element can be calculated in the path integral. So it can give you some idea about transport. This goes under the name fluctuation dissipation theorem. So I won't talk about this necessarily, but you'll see this stuff in textbooks.
Sorry, Roger, what's a dynamical susceptibility? What two quantities does that relate?
This relates the response of a magnetic. So if you have a spin sitting there and you probe it with a magnetic field, it's telling you about the response of the spin state to the field.
As a function of frequency? Or?
Frequency and momentum. Okay.
But it's so the frequency of, as you apply different frequencies to the magnetic field.
Yeah. You'll have different.
Looking at the momentum of your spin. So.
Yeah. Well. Yeah. So this operator. So you have spins in different spatial positions. Okay. So if you have spins in a system, okay, you'll have a lattice. Say they're on a lattice. You could have a lattice momentum associated with the wavelength of the spin. Spin response. So it's just a Fourier transform of this spatial position. If you have a single spin, you're only worried about the frequency response probably. But yeah, you imagine applying an AC field or something and you're asking about how the spin responds. That's the susceptibility. Yeah. So this is a common bulk measurement that people make in condensed matter. This type of susceptibility. Same with transport coefficients. I mean, you measure the transport coefficient by the response, say, of a material to some, I don't know, like a Hall voltage or something like that. But you would calculate the transport coefficients theoretically through basically a correlation function like this. That's the point I'm making. Is the correlation functions relate something that you measure, like in some sort of bulk setup, whether it be transport or response or something like that, to the path integral formulations. So if you're doing a theoretical analysis of some of these quantities, the path integral is what you want because you can calculate the correlation functions. And maybe the most obvious for any of you guys doing X-rays or neutrons is scattering experiments. Where you commonly measure what you might call a structure factor. Or a spectral, what did you call a spectral density function, I guess? depending on whether you're elastic or inelastic and so on. So I think the inelastic cross-section is a direct probe of the spectral density function. A of Q omega, you might call this thing. So if you do a scattering experiment, you go to the spallation source at Oak Ridge and you measure the spectral function. That spectral function can be calculated in a Hamiltonian model or in a low energy effective theory from a 2-point correlation function like this. So these are often called Green's functions or propagators. They're central objects when you study many body systems. And actually, there's a whole course we offer on Green's functions. I think it's called Green's functions. Elizabeth Nicol teaches it at Guelph. So I won't go into any more sort of detail about the relationship between correlation functions and response theory and so on. I forget the number of that course, but Elizabeth goes through in great detail the relationship between Green's functions and all these things. So all I want to do today is sort of discuss, I guess, the structure of the Green's function in the path integral representation, so that if you're interested, you can relate it, the path integral, to all of these quantities in some other course. So I want to start from, I want to imagine this path integral description of the partition function. But let me start by writing it back in the easy single particle case. And there's only one point I want to make with single particle path integral, and that's when we have time-dependent operators. The correlation functions that we're interested in are time-ordered. So let me start with, remember I called that propagator U, which had a functional integral over P and 1 over X. This is the Hamiltonian formulation. That's the time derivative of X there. And this is like the matrix element of the Hamiltonian at time t double prime. Yeah, so every textbook would call this like t naught and t final or something. That's why I have all the t double primes in there. So that was a single particle path integral. I mean, compared to what we've done in the many particle coherent state case, it's just essentially the same notation. We just replaced the p and the x with the field and its conjugate. Oh, and I wrote 2 conjugates here. That's not right. Only one of those is conjugate. So let's consider 2 operators. Yeah. So these things operate on 2 different times. I don't know if I need that. So just very generally, I'm constructing a 2-point correlation function like this for 2 different times. And in the path integral sense, where my time goes from t to t prime, which in the imaginary time path integral, remember, goes from tau equals 0 to beta. Let me order these times. So that t1 is greater than t2. So t1, so this operator occurs later in time than the operator associated with t2. And you can think of the Heisenberg picture if you want, in terms of what these operators might look like. So if I insert these in the path integral, then let's just look at the matrix element. Okay, let's look at the expectation value of the operator. So these are still operators. I'm constructing something like this expectation value. So I need to trace over the operators and then e to the minus beta h. So in the single particle path integral, I guess it's something like this, t to t prime. That's the matrix element we need to calculate. I'm just being very explicit about something that I think you'll find completely trivial. Let me break up that exponential. Okay, so the only difference between this and the path integral that I derive is the fact that I put these two operators in here. And one operates at t1 and one operates at t2, two different times. So t1, t prime. That operator acts there, e to the minus I over h bar. Then this will be, say, t2 to t1. Operator for t2. And then t to t2. So you can imagine, breaking up that exponential such that the operators are ordered according to the time in which they operate, t2, t2, t1, t1. And then imagine doing the discretization that gives us the path integral. Remember, we replace, we break up this exponential into a bunch of approximately commuting terms, insert resolutions to the identity. We do it in discrete time, and then we take a limit when delta t or epsilon or whatever I called it goes to 0. Right, so let's look at those discrete times. So call and let's call them Tm and Tn, T2. So then that matrix element, well, it's not strictly equal to, we have to take the limit, I'd say, but whatever. It's essentially the functional integral that we're used to by inserting all these resolutions of the identity. And now I'm going to have epsilon h. So we have all these products. Here's one resolution of the identity that we've inserted, which is what defines our discrete time. And here's my operator, x. That's m, so it's t1. Oh, got to put in my time evolution operator. Okay, epsilon is just that small parameter that goes to 0. Right, and we keep doing this. So I have an m, then I also have an n. I don't know. That's where my second operator occurs. I didn't label them, but that's the one that occurs at time 2. N minus 1, all the way down to x. All I'm doing is, to define the path integral, is taking the limit where this turns into a functional integral, right? So the point with looking at this in discrete time was just to drive home the fact that the path integral naturally time orders the operator product. So after, presumably this is a coherent state, right? So which means it's an eigenequation of the Hamiltonian operator, right? So then I can operate on this discrete time ket with the operator at its associated time and get out the matrix elements of the operators at T1 and T2. These can be different operators. I should have labeled them 1 and 2, but. And then the rest of the path integral is just like you remember. So T to T prime, dt double prime, P x minus h. And these things are no longer operators. These are C numbers. So all I'm trying to say is that in order for the operators to be replaced by the C numbers in the path integral, there's a certain order.
Where did the time integrals go?
I mean, just look way back at the single particle path integral. So I have this, I've taken this exponential and just divided it up into small discrete times. So there's like a delta tau or an epsilon or whatever I'm calling it. Yeah. So if it's discrete, then it's like a sum comes out in terms of a product out front of the exponential. And you have this product of all these times, you insert all these resolutions, the identity. So the only point I'm trying to make is that your operators operate on the time at which they're defined. And that I've defined T1 to be greater than T2. So when I pull them out of this path integral representation of all the operators in the exponential, that's the order that they occur in, naturally. You know what I mean?
Was the first inner product, does that implicitly have a time ordering operator then?
There's no implicit time ordering. The only time ordering I've defined is this thing, is the fact that the operators occur at different times. So, but what I've ended up with is a correlation function, expectation value that's time ordered. That's what I'm saying. This defines time ordering. So in order for these to be C numbers, we need implicitly they're time ordered by the path integral. Oops. So each operator acts on its associated resolution of the identity. When this thing's introduced, it means it yields a time-ordered product. So it's almost completely trivial. I mean, you're wondering why I'm writing it. Well, the reason is you'll often see a Green's function written in terms of a time-ordered, with an explicit time ordering operator in it. And the reason that a Green's function has a time ordering operator is just so that it's defined properly relative to, the path integral representation. So the time-ordered product is the time-ordered two-point correlation function is the quantity that response functions and all this other stuff should be evaluated in terms of. And if you take an Elizabeth's class, you'll discuss advanced and retarded Green functions and so on. All we're going to look at today is just a thermal Green function. Okay, so the thermal Green's function is the case when these operators, which again could be different, are just the field operators. So I'm calling them sidebar and psi. So when I have the two-point correlation function of field operators, and it's time ordered, that's the thermal Green function, if it's time ordered in imaginary time. I forget if it's green or greens. So the thermal Green function by definition, G, can have R positions, and we're in imaginary time. It'll be the expectation value of explicitly time-ordered product of operators. Tau. Okay, let's do it like this. Tau prime. Sure. So that time ordering operator means is that this correlation function two different R's, R prime, is this expectation value when, did I do this right? So tau has to be greater than tau prime. And you reverse the order. Good. So you'll often encounter this time ordering operator when you're asked to calculate a two-point correlation function. And the reason that, this is defined as the thermal Green's function with this time ordering operator is just so that the operators occur in the right position in the path integral. So there's nothing deeper than that about it. So all this formulation you'll do of analytical continuation and retarded and advanced Green's functions is just defined to give you a functional integral that's an expectation value that's time ordered in the functional integral. And so that Green function just looks like the many-body functional path integral analog of like that, of that thing over there for the single particle case. G. So it's normalized by the partition function, functional integral in the fields, and then your time ordered product. What did I call that thing? T. All right, that's the simplest way to write it. So like I say, it's the experimentalist's responsibility to somehow evaluate physical responses or to measure physical responses such that they correspond to this time-ordered product. And it's a theorist's responsibility to calculate this integral, basically. And that integral can be done exactly in the case when it's quadratic. And that's really all that field theorists know how to do, besides perturbation theory, is solve these quadratic integrals. So let's just specialize the action to the case where we have this quadratic Hamiltonian. And I'll just show you the procedure by which this Green's function's evaluated. And I'll skip a couple steps, but I'll at least give you the basic flavor of how these calculations are done. The path integral, the fields are, general for bosons or fermions, or just Grassmann. The eigenequation gives you Grassmann numbers if it's fermions. But let's forget about that and just look at bosons. So when things are quadratic, typically they're labeled with a naught subscript, which gives you an idea that in perturbation theory you'll have h naught plus h1 and so on. So let's see a non-interacting Hamiltonian in second quantization. We just have a number operator. And this will give you the matrix element if you have the proper coherent state. Right? You operate on the coherent state with that A dagger A, and you'll just get h tilde as which is a function of the field values. E minus the chemical potential and the field values at their different times and positions. And since it's the same operator, it's just the field and its conjugate at R and tau. That's an H. I don't know what happened. I don't know why I committed to these curly H's early on. H tilde. So all I've done is I'm substituting in a specific, call it H naught, non-interacting Hamiltonian into our path integral. And our goal would be to solve this green function to get to get something related to an experimental response function. And like all of these things, all of these types of integrals, the game's played much better if you go to Fourier space, so if you go to momentum space rather than position space. And that's especially well suited to the imaginary time path integral that's periodic in beta. So remember, when you're periodic in beta, you can introduce these Matsubara frequencies and write all of your fields in terms of their Fourier modes. So remember the Fourier transform that I wrote last time? The field at tau up to this normalization. It's just a Fourier transform over discrete frequencies. And the conjugate also sum over those frequencies. And then let's see, I omega n. So actually, when we write it like that, we haven't specialized the bosons yet. Because as you know, the difference between bosons and fermions in the Fourier representation, it's just the list of frequencies allowed. That's the Matsubara frequencies. So for this non-interacting Hamiltonian, the first thing you do is Fourier transform the action. And we'll get a representation of the two-point correlation function, or the green function, in Fourier space once we do that. So the action which was something like this, tau derivative of the field. So I have H naught here, non-interacting. So the way you do this, which is standard, and you'll do it like 100 times if you do this for a living, is you just substitute in the Fourier representation for the fields. So you notice here that you have a tau derivative. So really the only trick that's involved in doing this integral. So the tau derivative of phi of tau. So if you take a tau derivative, it just affects this exponential, pulls out minus I Matsubara frequency. And that's it. So you just get two terms in your Fourier transformed action. One that comes from this tau derivative, and one that comes from the non-interacting Hamiltonian. So then the action. We introduce a different index for the field and its conjugate. So one's n and one's n prime. So we'll call the conjugate n prime, I guess.
Omega n should be inside this one, no?
Oh yeah. Not rewriting it now. Okay, so that's the first term from the tau derivative. And then the second term. Well, you just have your Hamiltonian, which is written right here. Okay, so that's it. So then the next thing is you just basically have this inverse Fourier transform over tau, right? So you just use so let's see, I tau omega n minus omega n prime. So you have to have the normalization, then it's just delta omega n minus omega n prime. That just sets your indices on the sums to be the same. So like all of these things, all of these types of integrals, you only get one sum over frequencies, which contribute. So then the action written in terms of the Fourier modes of the field, there's still one sum. It's often written like this, and then it's minus I omega n plus the piece from the Hamiltonian. Whoop. So that'd be the action for, the path integral representation of a field theory of a non-interacting Hamiltonian. So as soon as you see kind of A dagger A in the Hamiltonian in second quantized notation, that's your action. And it's in Fourier space. So the only tricky thing is to remember that you have minus I omega n out in front of the Hamiltonian term. So you take this action, which has been Fourier transformed, and you can substitute this thing back into the functional integral form for the green function, and that'll let you solve for that green function in Fourier space. In order to do that, you also have to Fourier transform the functional integral representation of the green function. Okay. balancing G. So every time the field occurs, you have to plug in its Fourier representation. So to make a long story short, remember we're still calculating the same object as over there. I'll just put the tau labels on it. But now I have these frequency sums. One for the field, one for its conjugate. I have the partition function, which we'll just leave as arbitrary. And I have the functional integral. Got to worry about the Jacobian here. But I'm not going to worry about it. Then we have the two fields, which I've Fourier transformed now. It should be, how did I define this? Field first and its conjugate. So it should be like that. Okay. Then e to the minus action, which I've already Fourier transformed. And then from these fields, I still have I omega n tau. That one comes first. E to the minus I omega n. Oh, that one's plus because it's a conjugate. I got these backwards. So I can just label this one n prime tau prime. There. Okay, so without boring you, the way you do these functional integrals is the same way we just did the integral for the action. This is like the inverse Fourier transform. So you just have to know how to do, the functional integral generalization of the Gaussian integration. Okay, that's basically how these integrals are done. Because I'll look up your generalized Gaussian integration, and then generalize that one step more to functional integrals, which is non-trivial in some sense, but that's what mathematicians are for. So it's simple enough to sort of just look up this generalization. But just remember, it's a functional integral. And that Gaussian integral that you'll have to become comfortable with if you do this. But we won't do much more of this in this class. Is written over two variables, xi1 and xi2. The i's are there to remind you that this is a product of many integrals for each one. So it's similar to our functional integral with discrete variables. And this is like our partition function. I'll write the answer first. So it's the inverse matrix element of that thing, which is a real symmetric positive definite matrix. Real symmetric's fine. Positive definite means that I think is you have positive real numbers anytime I think this column vector is real. So it's real symmetric positive definite matrix. And these things are the linear algebra analogy to your wave function. So x is equal to, it's like, oh shit. You have this n component matrix, but you've transposed it to get the column vector. Actually, I just like opened a textbook and wrote that down. So that's the Gaussian, that's the expectation value. This is basically Wick's theorem. So just for some general, linear algebra problem, the Gaussian integral, and if you specialize this to the case that you are used to, you'll see your usual Gaussian integral in this. But the point is that what you get is the inverse matrix element operators, or the inverse matrix elements here. And so whenever you see this type of integral, you're going to get the inverse of this operator here. That's why the Green's function is defined like that, essentially. It's because it's well defined in terms of this Gaussian integral. The inverse operators happens to be this. If you had -1, if you had like an Ising model, which you'll do in 705, then you have an interaction matrix between all your lattice sites, all the spins on your lattice sites. And that would be your A. That's like what we call J. So all the Ising interactions give you the 2-point correlation function, or the Green's function. But you have to take their inverse matrix elements. And it's not the matrix element, it's not 1 over each matrix element generally. It's the inverse matrix's elements. But in this case, it just boils down to that expression. So our Green function, so if you're interested, you look up this generalization of the functional integral, but I think it's the least interesting thing. But somehow it's fundamental, I guess, because you get out this inverse element here. So the thing that we're calculating looks like the Fourier transform of this inverse matrix element that occurs in the action here. And one thing I've glossed over is that only one sum will contribute. And it's basically the same reason that only one omega n index contributes here. You get a delta function when you do this Gaussian integral. But if you define this object here as sort of the Fourier transform of G, so call it G I omega n, which is this thing here. then you'll get the expression that you might have seen before, that you'll see many times in Elizabeth's class. And that's just the frequency-dependent version, or the Fourier transform Green's function. It's just 1 over, basically, the argument of the action here in Fourier space. And this is important. This may be the most important expression that you get out of the path integral formulation experimentally, because these correlation functions in the frequency domain are typically what you're calculating experimentally. So this object that you're getting out from scattering experiments or from transport or whatever gives you some information about the spectral decomposition of the Hamiltonian, right? But it's buried in this denominator here. And because this is complex, the pole structure of this function gives you your spectrum of your energy spectrum of your Hamiltonian. So whenever you're doing a scattering experiment and you get out this type of Green's function, you have to analyze the pole structure. You have to do a complex analysis on the object. And because of what we just sort of derived, that this gives you the inverse. This gives you the spectrum in its pole structure. So that's the take-home message from all this. So that's why scattering experiments, neutron scattering and so on, that's why they're so remarkable. You cool a material down to very low temperature. You essentially scatter, you set up your scattering such that you're probing this frequency-dependent Green function. And you're getting information about the low energy, the low energy spectrum of the Hamiltonian. But it's the Hamiltonian, if you will, it's the effective description of the Hamiltonian in terms of second quantized operators. So it'll give you an idea about what A and A dagger are. It'll give you an idea about the structure of sort of the many-body theory that underlies the low energy excitations. So if it's a magnetic system and you're doing neutron scattering, you can be probing sort of the underlying dispersion of the quasi-particles and so on, just like you guys had quasi-particles, a quasi-particle description of the 1D transverse field Ising model. Those A's and A daggers would be the A's and A daggers that lead to the field operators that you would actually be probing with these types of scattering experiments. So, up to being lazy with that Gaussian integral, you basically derive this form of the Green's function, which is used all over the world in scattering experiments. Any questions about that? I think that's the simplest take-home sort of message from looking at these two-point correlators, is this connection between the pole structure and what you'll measure experimentally. But there's many other things. You can derive the Fermi or Bose distributions thermally from the Green's functions. But I don't know. This isn't a Green function class. So Elizabeth will do a lot of this stuff. And you can take Elizabeth's class and relate it to the path integral just through what we did today, I think. So I want to move on to something more fun. That's the spin coherent state path integral. Okay, so remember what we're doing here. Remember, the reason we have these field operators, is because we have a coherent state for bosons and fermions. We've developed it in analogy to the X and P path integral, the single particle path integral in time and momentum or position and momentum space. But spin's quite a bit different. And the path integral for spin looks very different, even though the motivation behind it is essentially the same. You want to have some sort of eigenstates that when you write a spin Hamiltonian, allow you to easily get out the eigenvalues of that Hamiltonian so that you can use it in this path integral. So it's not immediately obvious if you start thinking too deeply about angular momentum operators how that's going to pop out. So what we're going to do is we're just going to develop a path integral for a single spin. But the many-body generalization is the same as we many-body generalized the boson and fermion path integral. You just got to keep in mind the commutation relations. Why am I hesitating? Feynman could not construct a spin path integral. And I'm sure I spell his name. This is all due to Feynman. The single particle path integral was Feynman's, directly Feynman's construction. He thought about the spin path integral, but basically couldn't figure it out. And it wasn't until the late 80s, I think, that people really were comfortable with the spin path integral. The problem is, we don't have any analogy to like X and P. In conjugate momenta. So there's no analogy to what we just did. Here, this is completely analogous to X and P because it's like a field and its conjugate. So that's not as easy for spin. So something that's cool that I don't think I can do. I tried it last time I taught. It was a big mess. So you can construct a path integral ignoring spin quantization. And spin quantization will come out of the formalism. And this is related, and we'll see how the path integral gives rise to this geometrical phase and so on. So the geometrical phase, which will be defined, it's defined modulo something like 2 pi or 4 pi. I think in some deep sense is exactly the same thing as spin quantization. So if I'm really careful about this proof, I think I don't have to assume spin quantization, but I'm not going to actually try to be that careful. So I think we should just think of the spin path integral as an equivalent description of the quantum mechanics of essentially angular momentum. In the same way that I keep saying that the path integral description of, of single particles in X and P is just as fundamental as the operator description. So we got to start with figuring out what the coherent state is. It's the same as we wanted to figure out the coherent state for bosons and fermions. And I motivated, exactly the form for the coherent state that we wanted for bosons and fermions, in analogy to writing the Hamiltonian for X and P in terms of its matrix elements. So for the spin coherent state, somebody's done this. It's basically the same motivation, but the form of the coherent state just looks a little different. So let's just start with, a spin S particle. Where we have 3 spin components, equals, which are operators. And we'll take these operators and construct the path integral from them. And the operators obey the commutation relation. Let's see if I can screw this up. So it's I, J. You have to have that Levi-Civita symbol, so it's I, J, K. And then I, J, K. Okay, so we're starting from the commutation relation. And we also know from our elementary theory of angular momentum to choose a quantization axis. So we'll choose SZ. And then we define the eigen equation. For SZ with eigenvalue M. And for S squared. So the total angular momentum squared operator should be S plus 1. I think that's all I need. So the first step is to use these operators and construct an arbitrary rotation around some axis. Okay, so we're going to take a spin state and arbitrarily rotate it. And the reason is that in our path integral, we're going to start with spin states, and as we evolve in imaginary time, we're going to apply rotations essentially to the spin operator. That's what the path integral will look like. It'll look like all these different rotation operators in d+1 dimensional space. So any arbitrary rotation in 3-dimensional space can be parameterized by 3 Euler angles. And there's a standard way of doing this. And all you do is you take the classical rotation and just plop in the quantum mechanical operators. Okay, so any arbitrary rotation in spin space. So I'm going to call these angles chi, theta, and phi, which hopefully won't come back to bite me later. Yes. Okay, I think they're good. So what you need to do is construct, a single operator for a rotation on one axis, and then so call that your z-axis. Then another arbitrary rotation on y, then another arbitrary rotation on z, and you can do any arbitrary rotation in 3D or in 3 space with those 3 angles. So let me define that operator. So let me call the angle alpha and the axis J. And the operator for a clock, so it's a clockwise rotation by definition by that angle around axis J. Right, so that's the operator R, J alpha. I, J alpha. And that rotation actually defines the angular momentum component if you want. Okay? So that subscript's the component. It can be arbitrary, but because we understand how to deal with operators SZ, SX, SY, that's the axes that we'll choose, of course. That's only one rotation, clockwise around one axis. To get an arbitrary rotation, you need 3 of these things. And I'll call it R. So it's an operator still. And I'll use the Euler angles now. So chi, theta, phi. No subscript because it's the product of 3 rotations. So phi, z, theta, y. What's the last one? Chi. So it's zy and z again. Okay, hopefully you've seen that somewhere else before. So it's true, of course, in the classical theory of angular momentum and so on. And all we're doing is putting the operators z, y, and z in here. Okay, so this is the operator, or the operators that we'll use to construct the spin coherent state. So like I say, you want to think of somehow arbitrary rotations in some d+1 dimensional space. Okay, so in order to do that, we need to simplify basically the product of a rotation operator with the operator. So I'm not motivating the form for this spin coherent state. I'm just deriving it because I don't know how to motivate it. Okay? So somebody figured this out, and this is the best way to do it. So we need a few tools in our toolbox. So we need the commutation relations, we need these rotation operators, and we need an identity. Which is basically going to occur when I sandwich an operator in between 2 of these rotations. So I'll say plus here. So I have 2 indices, 2 axes, I and j, and they can't be the same. So I is not equal to j. Okay, so this identity is I, j, k. There's a sign. That comes from the commutation relation. J, I, j, k. So this is k sine phi. I won't prove this, but you can prove this, I think. So I think you can prove this if you just take this expression in terms of arbitrary operators x and y, and write out, expand all the exponentials, and you'll get something that looks like this. Oops, big Y. I don't know, apparently this is some standard thing that people use in combinatorics, but I hadn't seen it before this. I'll leave that to you. I'm not going to do that proof.
Is that similar to the Baker-Campbell story?
Yeah, it's curl.
Okay, so you've seen it before. So yeah, basically plug in the operators there, and you'll get this. And it's just because like cos is even and sine is odd. So when you start nesting all of these commutators, that even and oddness simplifies to this nice form here. Of phi. So that identity vastly simplifies things. So what we're going to do is use that identity to calculate R S Z R. R adjoint. I'll have to put on this side. And this will be the thing that allows us to calculate the spin coherent state. So I'll start with this next time. But what we're aiming for is something that looks like the total spin operator, dot product, with a unit vector of the final rotated spin. By the way, this spin coherent state is going to take me like 3 classes, so we have to get used to bailing on proofs halfway through the class. So this thing is the unit vector. And it's basically the operator S dot omega, which is the operator that we're going to construct a spin coherent state for. Okay? So it's going to be this thing, multiplied by, or operating on a spin coherent state that I'll call G, gives the eigen equation that we'll construct the path integral for. Okay? And you'll see the reason once we write the coherent state. But that's the weird thing about the spin coherent state is the operator that we're looking for looks something like this. Okay? So we'll do this proof at the start of next class, and then I think, yeah, we'll be able to write down the spin coherent state and then start plugging that into the path integral. Okay? And after we develop the path integral using this operator and the proper coherent state, then we can start looking at the geometric phases and so on. And this will all be sort of the single particle case. Okay, so I'll see you guys on Thursday, and we'll just continue with this.